Okay, so we were studying this mass oscillating back and forth on a spring. The mass has a mass m, the spring constant k. The spring constant indicates the stiffness of the spring, and the mass, of course, is an indication of like how much inertia, how much sluggishness the thing has going back and forth. And we were trying to show, hey, is this simple harmonic motion? Well, we know that the force that keeps pulling it back towards the center right here is this spring force right here. And that spring force is equal to negative kx, vectors here, because when x is positive out here, the force is in the negative direction, and when x is negative over here, the force would be in the positive direction. And if we want to prove that this is simple harmonic motion, what we have to show is that the acceleration towards the center is directly proportional to the displacement towards the center. And if you start off with Newton's second law and work it on down, you find out that, yeah, the acceleration is directly proportional to x. And basically the proportionality constant is negative k over m. So if you call that proportionality constant capital B, the proportionality constant capital B is equal to negative k over m. And it turns out that if you could find that proportionality constant, you'll be able to go on and write every single simple harmonic motion equation you need to know for that particular setup. So one equation that you'll need to know is the function x of t. This function should be set up so that if you put in the value of t, it'll immediately tell you the location of the mass on the spring. It'll tell you the position. So to find this function, we go back to Newton's second law, and we substitute in the spring force formula, Hooke's law, and we get a differential equation. It has a function x of t, and it has the second derivative of that same function. Now, sometimes we actually solve the differential equation by using like separation of variables. But in this case, all we did was we guessed. We took a guess what we think the solution to that equation is. And here was our guess right here. A represents the amplitude, or how far back the object was pulled to begin with. And omega here is another constant called the angular frequency. And it has to do with the timing of the oscillation back and forth. Well, if you take the derivative, and then you take the second derivative, and then you come back over here and you substitute those in, you'll have negative k times x, a cosine omega t equals m times the second derivative, which down here is negative a omega squared cosine omega t. The good news is we see, look, there is cosine here and cosine there. There's a good chance they are going to be equal to each other. But they're only equal to each other if this, there should be, the a's cancel out. Only if negative k is equal to m times negative omega squared. And I want to rewrite this. Negative omega squared equals negative k over m. Now this is really important because that proportionality constant was negative k over m. Remember, way back over here? Where is it? The proportionality constant between a and x was negative k over m. So once we have that, we can actually figure out what omega is going to be. Come on, Nelly. And if we solve this for omega, omega is equal to the square root of k over m. So now we know A is how far back you initially pull the object, and this constant omega happens to be equal to the square root of k over m when you're dealing with a mass on a spring. If you're dealing with a pendulum, which is what we're going to do next, omega will have a different value. Once you know what omega is, you could write down all the formulas you want to know for that particular motion. We know we have x of t equals a times cosine omega t. And I could write square root of k over m for omega, but usually people just write that on the side. With omega equal to the square root of k over m. And then if I take the derivative of that, I get the velocity function. And using the chain rule, that comes out negative a omega times sine of omega t. And then I can take the derivative again, and I get a of t is equal to negative a omega squared cosine omega t. So I have three describing formulas that tell us exactly what that mass on a spring is going to be doing. And the fourth and final formula you need to know is the period of the motion. Now we know that when omega t is equal to 2 pi, the cosine function went through one complete cycle. And when it goes through one complete cycle, that's when the lowercase t equals the capital T, the period. So omega capital T when lowercase t is equal to capital T, that's when the cycle repeats. So that's 2 pi for the cosine function. So if I solve this for period, I get period equals 2 pi over omega. So that's our final formula here. And this is just a recap of what we did yesterday. And for all of those, I could put in omega equals the square root of k over m if I want to be just more descriptive. But usually it's written there on the side like that. But let's just do it for one, just the last one, because it's the one we learned last year. We would have period equals 2 pi times 1 over omega. But another way of writing that is period equals 2 pi times, whatchamacallit, 1 over, in this case, omega is the square root of k over m. And another way of writing that is the period is equal to 2 pi square root of m over k. And that's the formula you learned in AP Course 1, the period of a mass on a spring formula. This year, we actually derived it. Once you know omega, you found all the formulas you need to describe the particular example of simple harmonic motion. And how do we find omega? Back over here. Let's see, where is it? We found that the proportionality constant here was negative k over m. But we're, let's see, where's omega? Oh. Right here. Negative k over m is equal to negative omega squared. If this is the proportionality constant from the beginning between a and x, the proportionality constant in the beginning between A and X is equal to negative omega squared. So here's the name of the game, people. We have all these formulas, and all we need to do is find omega for the particular setup, yes? How do we find omega? We first show that the acceleration is directly proportional to x. We find the proportionality constant, capital B, but that capital B right there is always equal to negative omega squared. Initially, we found capital B equal to negative k over m. And then later on, we found out that negative k over m had to be equal to negative omega squared. Once we find this, then we could use B equals negative omega squared to find omega. And then once we have omega, we could come back over here and we could write out all the different equations to guide that particular simple harmonic motion.